I still don't have the connection, so I wanted to mention an interactive activity that some of you pointed out, but it's too early. Let's postpone it because I need a connection to do that. And so let's make a summary, a brief summary. I asked you to have a look at the linear reservoir, and given that some of you reported to me that you already learned something about the linear reservoir in your previous subjects, I asked you if you could have a look at it. So can I get a confirmation from you that you are fine with the linear reservoir and you are autonomously capable of, if requested at the exam, to develop the integration according to these equations, and you can get to this final result, including the version with constant rainfall. Is it fine? Okay. If not, please let me know, maybe later. I just want to point out that the linear reservoir is a very simple model, which is nevertheless quite used in hydrology. It's used mainly for flood modeling, not really for water resources management. And the reason why it's not used is that for water resources management is that in its current form, the form that you see here, the only input that is considered to the model is rainfall. And there is no means here to take into account other losses besides the outflow from the bottom reservoir, which means that you don't consider losses like evapotranspiration, which it's an important component of the water balance. There are situations in which you can neglect evapotranspiration, and these situations are those where the outflow dominates, the river flow dominates over other water losses. So if you look at the reservoir, the outflow from the reservoir can be considered as a water loss. Indeed, it's not a water loss, it's a runoff in the river, it's flow in the river, but it can be considered a loss from the content of the reservoir, like evapotranspiration is. If you look at a catchment and you look at the water that is going out from the catchment, you see, of course, the runoff from the river, the flow in the river, and also you see evapotranspiration. You can neglect evapotranspiration when other flows dominate over evapotranspiration. And in this case, the other flow that you are considering is river flow. And what are the conditions where river flow dominates over other flows? These conditions are those in which the river flow is high. Of course, it's intuition that suggests you that when a river flow is high, it's very relevant. You can neglect other flows. So during floods, of course, you have a high river flow, and then you can neglect evapotranspiration. Also, there is another reason. During floods, usually you have bad weather, and in bad weather you have low temperature. It's not really a very hot day during floods, and therefore evapotranspiration is lower. But the main reason is that it's much lower than the river flow. But if you look at the typical situation of water resources management, critical situations, these are during drought conditions. And in drought condition, you have the river flow that is very limited, and in this case, you can't neglect evapotranspiration. This is the main reason why the linear reservoir is not used in this form as a model for water resources management. And you may say, okay, but I can take into account evapotranspiration in some way. Of course, we could estimate evapotranspiration. We can understand our intuition suggests that there might be a way to estimate the flow due to evapotranspiration, and we could consider that flow here. But if you include another loss term, and in particular evapotranspiration, this term is likely to be not linearly related to the storage, and therefore the model is no more linear, it's no more a linear reservoir. In order to overcome this limitation of the linear reservoir, I'm not sure, yeah, it's here, some non-linear forms have been proposed of the same model. We are not discussing non-linear formulations of the bucket model. Bucket because it's a tank model. It's still assimilating the catchment to a tank. We are not discussing these non-linear forms because it goes beyond our purpose. But we will discuss another non-linear model shortly. And I just would like to say that it's in principle easy to modify the linear reservoir in order to include other flows. For instance, in this case, there is not only a bottom discharge, but there are other discharges that are activated when the storage in the reservoir exceeds a threshold. This is a reasonable assumption. It's in principle easy to introduce these additional flows in the same way you can introduce evapotranspiration. The only problem is that the model becomes non-linear. Even in this case, you see that if you introduce additional flows, additional discharges that are activated when the storage exceeds a threshold, like here, this is activated when you get with the storage here, this is activated when you get here, and in the current configuration you see two storages that are activated, given this, two flows, discharges that are activated given this storage, and the third one that is not yet activated. So, if you introduce such a conceptual model, this is non-linear, it's not linear. And the reason is that there is no linear relationship between outflow from the tank and storage. If you fix thresholds, it's non-linear because it is something like this. If you want to show the dependence between storage and outflow from the tank, in the linear reservoir you have something like this. And the slope of this rectilinear segment is dictated by K. K is the constant that is introduced to it's W divided by K. The constant that is introduced in order to relate outflow to storage. So K dictates the slope of this rectilinear segment, linear segment. And if you introduce flows that are activated after a certain threshold, what happens is that you have zero outflow up to a storage that is I indicated here with W prime, which corresponds to the level of the first discharge. And then it may be a linear relationship. And then, okay, let's see. A linear relationship with the reduced slope. And then you get to a volume that we can indicate, a storage that we can denote as W double prime, where the second discharge is activated. And therefore, if I put W double prime here, what happens is that by activating the second storage, the relationship between the second discharge, by activating the second discharge, the relationship between discharge and storage becomes steeper. Slope increases. So if we stop here and we forget about the third one, you see that the relationship between flow and storage, it's no more described by a rectilinear segment. It's piecewise rectilinear in this case. Piecewise means it's a composition of rectilinear segments, but it's the moral of the story is that it's not rectilinear anymore, which means that it's not the model, it's not linear. By the way, keep in mind what is a linear function. It is described in my web pages, and it may be a question at the exam. What is a linear function? You may say two things. The first one is descriptive, and you may say that a linear function is described by a rectilinear segment, but there is a mathematical definition which you should remember, which is resembled by two conditions. A function is linear if and only if these two conditions apply. One, f of ax is equal to a fx. This is the first condition. And then there is a second condition, fa plus b is equal to fa plus fb. Remember these. And in particular, the second condition is the superimposition principle, which in Italian is principio di sovrapposizione degli effetti. So if you introduce these modifications, the moral of the story is that the model becomes nonlinear.
This condition is a minus x.
Sorry, the first condition is?
A minus x.
No, it's a times x. It's a multiplicative condition. Okay. Let's move forward by considering another model. And this is quite technical. And the reason why I am discussing this model is that I think it is extremely interesting because it is more and more efficient than the linear reservoir. It allows us to include evapotranspiration. And it's widely applied in hydrology. We are considering only these models that I mentioned so far. So rational formula, in order to deductively assess water resources availability, we're only considering these models that I mentioned so far. The rational formula, the linear reservoir, the nonlinear reservoir without any analytical derivation, and IMOD. IMOD stands for, it's an acronym that stands for Hydrologic Modeling or Hydrological Modeling. Hydrologic is US English, hydrological is UK English. So, what is the reason why we need additional models besides the linear reservoir and the nonlinear reservoir. The reason is that the linear reservoir has the limitation that I already discussed, and in particular the fact that you are not considering additional water losses besides the river flow, and therefore it's not very useful for water resources management. This is for the linear reservoir. The nonlinear reservoir, by fixing these thresholds, gives simulation of the hydrograph that is not very smooth. So basically with the nonlinear reservoir, you may try, because you may have the capability with a computer model to simulate with the nonlinear reservoir, and you would notice that the hydrograph, instead of being regularly shaped, a typical hydrograph is like this. If you simulate with the nonlinear reservoir, what happens is that you have a simulation that is something like this, with a sudden change of slope of the hydrograph, and the same when you basically simulate the recessing limb. So instead of having a smooth behavior, there is a behavior that is characterized by sudden changes of the slope of the limbs. This is the raising limb. And this is the recessing limb. And the reason why you have sudden changes of the slope of the limbs is that when you activate additional flows, additional discharges, you have a sudden change of the hydrograph behavior. So basically, it was felt when dealing with hydrological modeling that we needed something that gives a smoother representation. And also, it was felt that we needed to take into account an important feature of the runoff generation process, which is spatial variability. Spatial variability is extremely important in hydrological modeling. If you think of the models that we considered so far, they assimilate the catchment to a tank with a unique input rainfall, which is implicitly assumed to be spatially constant over the catchment, over the tank. You have a unique value of rainfall, while over a catchment you can easily understand that you don't have constant rainfall, constant in space. Rainfall is varying in space, we know that. And we know that it's especially varying when the duration of rainfall is short. When the duration is short, we already said that the intensity is higher and spatial variability is more evident. And we can experience this when we drive with our car during a storm. We experience that there are sudden changes of rainfall intensity. Even if we move like 100 meters away, there are sudden changes, which means that neglecting spatial variability of rainfall, it's something that it's a coarse approximation. The same thing if we assume that the runoff generation process is not spatially variable, as we do in the linear reservoir, we make an approximation. In the linear reservoir, we assume that the river flow is just related to storage. It's just related to storage. And you see this representation, it's not spatially variable. It doesn't take into account spatial variability. Indeed, if you look at a catchment, at the complexity of a catchment, you may have areas, and if you get a rainfall over there, okay, let's assume that rainfall is partially constant, so let's neglect the rainfall variability in space, but still you may have areas in the catchment that absorb completely rainfall and areas that are not absorbing. And when is an area absorbing rainfall? When infiltration is higher than rainfall. So everything that falls over the catchment in terms of water is absorbed by the soil through infiltration, which means that the soil is not saturated. If you have areas that are completely saturated, you understand that everything that rains over there flows over the ground, doesn't infiltrate. And these processes are spatially variable, because while it rains, you get areas that are easily saturated, like close to rivers. In the bottom of valleys, you have more water available because you are close to the river. So the soil gets more easily saturated, while if you go over the hill slope, you have soil that is far from the river. It's steeper, the hill slope, and therefore you have more underground flow that makes soil storage free. And therefore the areas are typically not saturated. And if you go up in the mountains, it's more likely that you get rocky soils that don't absorb water and they get very easily saturated. So you understand that everything is spatially variable. So hydrologists understood that the linear reservoir, by not taking into account spatial variability, is providing a coarse approximation. And therefore, they tried to devise models that allow to take into account spatial variability, of course, which is heterogeneity. Of course, this is complicated, because in order to fully take into account spatial variability, you would need to know the catchment in detail. In any location of the catchment, you would need to know what is the soil type, what is the lithology and geology, everything, what is rainfall at the local level, everything. This is very complicated. So, of course, it was a problem, and hydrologists tried to overcome this problem. So the question was, how can we take into account in some way spatial variability without making the model too complicated, without making the model too demanding in terms of required information? And one possible solution is IMOD. IMOD, I think, was a brilliant idea, because as you will see, it allows us to introduce a simplified way to take into account spatial variability. Okay, so let's introduce IMOD. First, let's start by assuming that any location in a catchment is characterized by a potential storage, a maximum storage. It means that when it rains, any location can potentially absorb a quantity of water. And let's indicate this quantity of water, this storage, with a length, which is storage per unit area. So storage by definition is a volume, but if we indicate the storage per unit area, it becomes a length. And therefore, any location is characterized by a storage expressed as a length, which is varying over the catchment. We can identify a max value of this storage, which we indicate with C max. And then, over the catchment, if you get a location that we call location I, where I is an index that in general it's varying, describing the spatial coordinate. Typically, if you look at the catchment map, I, instead of being one index, it will be composed by two coordinates, but let's indicate for simplicity a location, a given location as location I. We can say that this location is characterized by a potential storage, which is Ci. What does it mean, a potential storage? It means that if it rains over I, water is absorbed, so no surface runoff is originated, and rain is stored in the location I, and therefore the storage increases. This storage is time dependent. It increases time dependent because while it rains, water is absorbed and the storage increases up to a value which is Ci, which is the max. When storage gets to the value Ci, location I becomes saturated, and therefore any subsequent rainfall is not absorbed. Any subsequent rainfall flows over the ground and contributes to river flow. This is the assumption of the model, the idea. And Ci, as I said, is variable. We already know, because we made this consideration a few minutes ago, that it's impossible to estimate Ci for any location in the catchment. But we can estimate in some way for a given storage C star, a given value of storage C star, we can understand that if we fix that value of storage, there might be location in the catchment, locations where potential storage is lower than C star, and locations, other locations, where potential storage is higher than C star. Of course, C star is included in the range 0, minor or equal than C star, minor or equal than C max. So if we get this C star, which is in between 0 and C max, we can easily understand that there are locations, I repeat, in the catchment where the potential storage is lower or equal than C star, other locations that are characterized by a higher potential storage. Indeed, if I was able to estimate what is the portion of the catchment in terms of percentage where storage is less than C star, and therefore the portion of the catchment where the storage is higher than C star, I could say that I don't care about where these locations are. What matters to me is just to know the extension of the catchment where storage is lower or higher than C star. Let me try to depict on this catchment on another sketch what I mean. Let's fix C star, and let's identify over this catchment, let's put the river network like this in a simplified way. Let's identify over the catchment the areas where potential storage is lower than C star. For the consideration that I made before, these areas probably are close to the river, and therefore it may be something like this. And also some areas close to the higher mountains, something like this. These areas are not necessarily connected. maybe another one here. But really, I don't care where these areas are. If I was able to identify what is the percentage of the whole extension of the catchment covered by these areas where storage is lower than C star, it would be fine. In this case, probably this percentage, which I can indicate with the symbol F C star, may be something like 50%, so 0.5. Maybe, I'm just guessing, based on the drawing that I just made. Now I realize that here C star was I treated it as not as a subscript, not as a superscript, but as a subscript. So don't be concerned by that. It's just a small difference, okay? So if I was able to estimate for a given value of C star, for any potential value of C star, this percentage of areas, I would be fine, because I could assume that what rains over there is transformed in river flow. What rains in the areas that have higher storage is absorbed. And therefore I could easily compute river flow step by step, as we will see. Because why I say step by step? Because of course the extension of this area is dynamically varying. While it rains at the beginning of the rainfall event, probably the extension of the areas where storage is lower than current storage, it's low because the catchment is dry. And then while it rains, the catchment gets more water, and therefore the areas where storage is lower than the current storage is increasing, because storage is in the catchment is increasing while it rains. So this area is dynamically varying as C star varies in time. But we will discuss this in 5 minutes. What is important for now is that you get this concept for a given value of C star. Let's consider it fixed so far. If I was able to estimate the portion of the catchment where storage is lower, then I could easily compute the river flow. So what I need is a function f C star, a generic function f C star. This is what I need, because this value was just a guess. I need an analytical function, f C star, and therefore something that I could write in this way in general. I need a function f of C star expressed in the form of an analytical relationship. Look at the difference between the capital F, which means a well-defined form, and the lowercase f, which is a generic analytical relationship. I need to give a shape to lowercase f. Okay, so what is a possible shape? It's what you see written here. Let me introduce it. Of course, what is the requirement for this function? The requirement is that as C star is varying in its range of definition, f C star, it's a percentage, should vary between 0 and 1. In some way. Okay, let's introduce it. Let's try with this one. F C star is equal to 1 minus C star divided by C max to the exponent beta k. Let's hope that my memory works here. Okay. Is it true that this is varying from 0 and 1? Is it true that f is varying from 0 and 1? Let's see. Let's suppose that C star is equal to 0. If it is equal to 0, the value between around parentheses becomes 1. Whatever is beta k, it remains 1. And therefore it's 1 minus 1 is 0. What does it mean? What does it mean that F0 is equal to 0? It means that, remember what is giving to you this relationship. It gives to you the percentage, not the percentage, but in a relative terms, so the extension of the catchment area where storage is lower or equal than 0. Of course, it can't be other than 0 because storage cannot be negative. So the storage, the percentage of the area where storage is lower or equal to 0 is just 0. Okay? Now let's suppose that C star is equal to C max. If it's equal to C max, the quantity between parentheses goes to 0. 0 to the power of beta k is 0. And therefore F C max is equal to 1. Again, what is the percentage of the area of the catchment where storage is lower or equal than C max? Everywhere is lower or equal than C max, and therefore it's 1. So this function is varying from 0 to 1, which is fine. Look, this function could have a different shape. This is just one possibility. And the different shape could also be that it's not varying from 0 to 1, but it's varying from 0.2 to 1, or from, not necessarily it should start from 0. This relationship here